Okay, so here's where we were last time. We were talking about, well, we actually left off just before this, I guess. But so, new topic for today. You're talking about dot products. So I hope you all remember the dot product. This is the formula. This is a standard linear algebra Math219 thing, so presumably you already know most of what you need to know about dot products. And again, keep in mind, tough choices and all that, and I don't have time to cover everything. So since presumably y'all have seen a lot about the dot product before, I'm going to be very picky and choosy about what I spend time on. So review what's in the book. Make sure you're good with all of that. The couple of things I do want to talk about. First, a little bit of terminology. I feel like our book is a little sloppy in its use of certain key words. It's terminology, but still, perpendicularity and orthogonality, I don't think should be viewed as being the same thing. There's something subtly but importantly different about them. So along those lines, let me point out there is a geometric idea in play here. Namely, if you talk about two directions in space as being perpendicular, what we mean is there's a right angle. Right? So this idea of a right angle between two directions is an intrinsically geometric idea. Now, there is another idea in play here, and that is this, what I'm going to call a fundamentally algebraic idea. This idea that you could have two vectors with dot product equal to 0. That's algebra, right? Dot product is an algebraic construction. Something equaling 0 is an algebraic statement. This is all algebra here. So these two ideas, the geometric one and the algebraic one, are closely related, very closely related. They're not the same. And when you have two concepts that are nearly the same but not quite, there's a strong temptation to use the same word to describe them both. But when you use the same word to describe them both, that makes it impossible to talk about how they are a little different. And they are, importantly, a little different. So in particular, this idea of perpendicularity, this geometric concept of a right angle, only makes sense if you're talking about non-zero vectors. Is the zero vector perpendicular to anything, really? It doesn't really make any sense. It doesn't point in a direction, so that direction can't make a right angle with anything. Does that make sense? So, whereas, by contrast, well, let me do it like this. The algebraic version of this dot product being 0, yeah, sure, you could plug in the u or v, either one or even both could be 0. Cool, whatever. There's no problem there. Right? So again, we have these two different ideas that apply in different cases. Technically, I mean, mostly the same, but a little bit of difference. So I feel like we need two words. We have two concepts, we have two words. We should pair them up. So I use perpendicularity to refer to this idea of a right angle. And I do my best, right? Mess up sometimes. I try to use the word orthogonality when I'm talking about this algebraic idea of a dot product being 0. So perpendicular vectors are always orthogonal, but orthogonal vectors are not necessarily perpendicular. Okay. All right, does that make sense to everybody? Is everybody happy? Make sure to give this a little bit of thought and sort that out in your minds and make sure that makes sense. Okay, moving along. Old news, I hope you've seen this before. I presume you have. If you have a non-zero vector, v, you can define a unique unit vector pointing in the same direction by this lovely little convenient formula right here. All you got to do is take that non-zero vector defining your direction in the first place and divide it by its own magnitude. Nothing to it. Pretty easy to persuade yourself this is going to work. Easy though it is, it turns out this is actually bonkers useful. We're going to be doing this kind of thing a lot. Very often we just need a unit vector pointing in a certain direction. This little construction will always do it for us. Is that cool? All right. Right. Alrighty, so new idea of something called a component. If you have a direction, specifically a direction that's defined by a vector, not necessarily a unit vector, just any vector, whatever. This direction might be, for whatever reason, the only direction you actually care about. And you're interested in, for example, some other vector, it points off in some way, but I only really care about the extent to which it points in that direction. For example, maybe we're playing football and the ball was here, and then after, somebody threw the ball, got tackled, whatever, and then it lands there. So how many yards did that play gain? Did it gain this many yards? No, not at all. Right? That's no fair. Right? You can't just run sideways and call that a gain of yardage. It's not how it works. You only get yardage in the relevant direction. It's only how far this sort of component in the direction of the vector defining the direction that we actually care about. And to the extent that you're talking about something that's perpendicular, all this perpendicular stuff we just ignore. Okay, so that's the big idea. This is called a component. Notice that it's a scalar. Right? Because it's a let me say something that's a little bit wrong, and then I'm going to correct myself. It's a scalar because it's a distance, right? It's how far is it from there to there? So what I've described here, not a vector. I'm not interested in the vector that would be described by this purple thing, just the scalar. Okay, now let me correct that. It's not a distance. It looks like a distance. It's closely related to a distance. Unfortunately, distances are intrinsically positive. The word distance is positive, right? You can't take miles off of your odometer by driving backwards, right? The distance from any location to any other location, never negative. But this could be, right? It could be. I mean, again, you're playing football. If you get sacked, you lose yardage. Right? Your gain of yardage is negative. So we do need this to be allowed to be negative, and so we can't technically call it a distance. Okay, now how do we compute this? No problem. Pretty easy to notice. Let me clean up my picture here. That component and the magnitude of the W vector are part of a right triangle on which I can do some trig, which makes this fraction the cosine of that angle. And once you write that down, you can just solve for the component. A little bit of easy algebra. There's the component. And if you want to simplify this formula, there is something unfortunate about this formula. You notice that there's a cosine in it. That's weird. I might not even know that angle. So the clever move here, very clever move, is to observe that I can take that and I can multiply and divide by the same thing. I'm going to multiply and divide by the magnitude of V. Seems like an arbitrary and weird thing to do, but you got to give me it's perfectly legal. Multiply and divide by the same thing. And having done that, notice my numerator becomes exactly a dot product, which is super handy. And as such, then, I now have an easier formula for how to compute the component. I can compute the component with dot products. It almost seems like a magic trick. Hey, wait a minute, where did the trig go? Right? And the answer is the trig is hiding inside of both sides of this equation. There's trig in what that component is, and the exact same trig is inside of what that dot product is. So, convenient little relationship. Everybody all right?
So it's a scalar too, right?
Yeah, absolutely. Yep. All right. Okay. So handy formula. Now there's an even handier version in my opinion, and that is to notice that right here I've got v divided by the magnitude of v. That's a unit vector. So I can rewrite this expression as that. And this leads to what I think is the most convenient, let's see how to say this, the most convenient to remember formula for a component. By this little pithy little phrase, components are dot products with unit vectors. Right? Rolls off the tongue really nicely. If you want to compute the component of a vector W, great. Take that vector W, dot it with the unit vector pointing in the direction that you care about. Everybody happy? All right. Oops. Okay, now here is a related idea. By the way, is it just me or is it a little muggy in here? It's really muggy, isn't it? Okay, I think, give me a second here. I think I can just turn this. Sorry. You may have better eyes than I do. Can you read what? Does it have a number in there?
75.
75. Okay, good lord. Okay, now what does it say?
70.
That'll be better. Okay. Okay, so closely related idea, and that is the idea of a projection. Okay, so projection. Here we go. My gosh, it's a pretty similar looking picture, isn't it? Looks almost exactly the same. Same little triangle, same sort of, well, there was a vector that I'm interested only in the extent, in some sense, to which it points in a direction or something kind of like that. And so what is the difference here? The difference is that this thing I'm interested in, the projection, is a vector, not a scalar. Why? Well, because life is weird, and sometimes you need the vector that is this, side of the triangle in this picture, and sometimes you don't need the vector. Sometimes you need the scalar. Different tools for different circumstances. So this one, being a vector, I can write it down by a nice little observation. One first observation I'll say is it's easy to write down the unit vector. The unit vector u that points in the direction that projection is. Okay. And then, now again, forgive sloppy terminology here, I'm going to say magnitude. That's not quite right, but how far this is, you're going to want to say, again, not really quite right, but we'll come back and fix that in a second, is just the component. And we've already got a formula for the component. Dot product with the unit vector. Right, now let me fix my sloppiness. This, what I have in green here, it's not a distance. Right, it's a scalar. It could be negative. If it's negative, the projection's going the other way because after all, the W would be over here, and it really would be literally a negative multiple there. Right? So intuition-wise, it's fine to think of this as kind of like a magnitude, but you have to keep in mind it's not an intrinsically positive thing like a magnitude is, like a distance is. Anyway, nice little convenient punchline. The projection is, let's see here, the projection is this product of those two things. Everybody on board? Okay. All right. Now, the book has a different formula. It's morally equivalent, but it's a little bit different. The book points out that, hey, we have a formula for that unit vector. Right? The unit vector is v divided by the magnitude of v. Rewrite like so. And then the book further observes that, hey, when you have a magnitude squared is a self-dot product. And so, alternative formula, take your pick. Either of these is fine, I suppose. But the projection that we previously wrote down with that formula, you can instead write it down with this formula. So like I say, take your pick. Now, the book goes with this one. There is something I don't like about this formula. It is giving too much attention, in my opinion, to the v vector. V's job, really, was just to define a direction. The fact that v has a magnitude that isn't 1 serves no purpose here. And there's something, in some sense, awkward about writing down your answer in terms of something, part of which is irrelevant. Right? So I think there's something much better about this formula. U is a unit vector. It does only one thing, and that is describe a direction. That's all we needed it to do. Right? And then furthermore, notice that everything that I have up here in this formula is meaningful. That is the component. That is the direction, thought of as a unit vector. Everything up here is a meaningful thing. Down here, the magnitude of that vector v is just irrelevant to the problem. Why are we talking about something that we don't need? And then even worse, this thing right here, it's not that it isn't a thing, it's just that it's not a particularly natural thing. So I think this formula is not only a little bigger, a little bit more to memorize, it's also a little bit more unnatural. And so, I don't really care for it. I have a strong preference myself for this formula up here. Does everybody see my rationale? All right. Okay, last quick reference, and then we're going to move on to the next section. Again, tough choices. Wish this was a year-long class, but it's not. So certain things I'm going to have to leave out. There are some nice examples in the book that show how you can use vector algebra to answer interesting questions about plane geometry. So things that you can do in a high school geometry class, you can do much more nicely with vector algebra. So there's a couple of examples in the book. Take a look. They're highly readable, I think. I don't think you'll have any trouble. And these will apply to at least one homework exercise. So you definitely want to look at those examples in the book and then try to, kind of use those sort of same ideas. But again, I think this is all pretty straightforward. That said, as always, if you get stuck on any of this stuff that I've just, very quickly, hardly, waved my hands at, come to office hours and I'm happy to help out. No problem. Okay. All right. So, new topic. We're going to talk about the cross product. Again, I hope y'all have seen the cross product at least somewhat before. I think I understand that our linear algebra classes are, they discuss some of it, but really not as much as we need for y'all to know. So I'm going to go over all this stuff. I am going to point out a couple of things. First of all, tough choices and all that. There are a lot of little facts in this section that you do need to know. There are a lot of proofs of these facts that are in my notes. I am absolving you of responsibility for the proofs. You don't need to know the proofs, and as such, I am not going to talk about the proofs. This makes me sad. They're lovely proofs. They're wonderful, right? They're very nice. They're nice little mathematical weightlifting where if you read those proofs, just the understanding of the proofs will help you understand the intuition for the geometry of cross product and related objects itself. So it's not that you should ignore it, right? I encourage you to read them, but I don't have time to talk about it in class, and I don't feel good about holding y'all responsible for proofs that I don't talk about. So they're just kind of, I don't really have much of a choice there. I just can't leave them in the course. Okay, so second thing I wanted to mention, there's a bunch of ideas in here that relate to a bunch of other ideas, and golly, there's bazillions of different ways to order these ideas as we go through this section. Different books make different choices as to what do they start with, and then how do they make their way through and touch all of the facts in question. These different choices of where to start and how to go have different pros and cons. The book has made a choice that is a great choice from a certain point of view. I'm going to make a different choice because we have a different set of considerations. And so what you're going to find is that the presentation I'm going to give here is going to look pretty different from what's in the book. We are going to talk, I believe, about all the same facts. We're just going to kind of work our way through them differently. For what it's worth, the order that I do this stuff in and the proofs that I supply, I think will give you the maximum amount of geometric intuition. That was my goal in deciding how to order these ideas. Maximum geometric intuition. The book's author, if she were here, would very correctly quibble that there's a pretty gaping hole in the presentation I'm going to give. There's the little matter of, I'm not going to really prove all these facts, right? So, like I say, pros and cons. Okay. Here we go. I'm going to start off by talking about a pair. Whoops. What's going on here? Where's my stylus? Oh, my stylus ran out of battery. Okay. Give me a second. I'm just going to plug this in. Sorry, I thought this might happen. This is a new stylus. Still getting the hang of its battery lifespan. I believe I could just plug it in like this. There we go. Okay. And I will use the other stylus. Okay, so let me make sure this is working. Yeah, there we go. Oh, and this is the one that doesn't, oh my gosh. The eraser on this is abysmal. Okay. Okay, so I want to talk about pairs of vectors in R2 specifically. This is going to end up being kind of a segue into what we're actually, the main thing that we're going to be talking about here. Okay, two vectors in R2. All right, that... Golly, I really can't see where the eraser button is. There it is. Okay, so I say here an ordered list. That's actually, I don't really need to say ordered. List implies an order, right? If you have a list of things, one of them is written first, the next one is written second. The order is implicit in how it's written down. So that said, I put ordered here just as a reminder, but we're going to be thinking of A here as being first. We're going to think of B as being second. Okay. All right. That said, how would I geometrically describe this order? Is there anything intrinsically geometric about this order? Now, there's different ways that you can answer that question, most of which end up being not that interesting. For reasons that will become clear in just a moment, there is one way to answer this question that actually is pretty doggone interesting. And so that's what I'm going to talk about here. And specifically, notice that whichever vector you've written first, whichever vector you've written second, right? If A is first and B is second, then if you will, the process of starting with the first and going to the second is intrinsically counterclockwise here, as I have those vectors drawn on the left. Everybody see what I mean? Counterclockwise. Now, of course, it doesn't have to be that these are the vectors in question. What if A was here, A still being first? What if B was way over here this time, B still being second? Well, now, the same list, A first, B second, is now clockwise. Right, and this is kind of, generically, these are the two possibilities. Most of the time, if you have a pair of vectors and you have to decide which one's first, which one's second, it's going to either be clockwise or counterclockwise. Does that make sense to everybody? Okay. All right. Now, annoyingly, yeah, it's possible, I suppose, that the first vector and the second vector will be scalar multiples of each other. Ugh, that's irritating, right? What are the odds? But this could happen, in which case, well, it's not really clockwise or counterclockwise, either one. You know what I mean? And then there's other possibility. What if A was the 0 vector? Again, there's no direction to talk about. You can't say clockwise or counterclockwise. What if A and B pointed in exactly opposite directions? Well, again, it just kind of doesn't make any geometric sense. Good news. All of these other cases come about when the pair of vectors is linearly dependent. So I'm just going to lump them all together. They're kind of annoying anyway, and we're going to call that third case just linearly dependent. So here's our three possibilities. If you have a list of two vectors in R2, that list is either clockwise, counterclockwise, or dependent. Happy? All right, now, is this natural or is this arbitrary? It's actually pretty natural. Not hard to persuade yourself. These two things are mirror images of each other, right? If you have a list, as you'll see here, A, B, counterclockwise, if you take the mirror images over here, clockwise, right? So these are mirror images of each other, or said differently, if you reflect both of the vectors in your list, the resulting list changes its order. Okay. All right. If you swap out the positions of the vector in the list, if you take the first vector and make it second, and the second vector and make it first, right, turns AB into BA. That turns, well, let's see here. Oh, whoops, I want to be in the highlighter mode. Highlighter mode. There we go. A to B is counterclockwise, right? But the new list, B to A, clockwise. So trading trading the two vectors' positions in the list changes the order. Nice, simple. This is not a sometimes or a most of the time. It's always. Okay. All right. The order is independent of rotations. If you take your pair of vectors and if you just rotate everything, that results in a new list of vectors. If the first list was counterclockwise, the second list is counterclockwise. A sort of a real-world version of this is that if you look at the second hand on a clock that has an analog face and see which direction the second hand is going, if you turn your head to the side a little bit, it's still going the same way, right? Rotations just don't matter. Okay, let's see here. Here we go. All right, so that was a segue to allow me to talk about an analogous idea in 3 dimensions. So now instead of 2 vectors in 2 dimensions, I'm going to talk about 3 vectors in 3 dimensions. And it's tempting to say, okay, well, we want to. What would counterclockwise look like? What would clockwise look like? And that's we're not going to be that lucky, unfortunately. But there is something analogous to clockwise, counterclockwise that we just don't have quite as much familiarity with, but nevertheless a little bit of familiarity. It's going to take me a bit to explain exactly what I mean by right-handed. Give me a second to talk through that. Here's what we mean by a right-handed list. Now keep in mind, very important, whatever vector is listed first, I think of as being first. And again, second, and third. Okay, so with this in mind, here's the convention. There's an arbitrariness to this convention. There's a lot of stuff in math that's arbitrary but standard. We have to kind of have a foot in the door to be able to do certain things. Okay, so here's the arbitrary rule. Right hand, index finger, whichever vector is listed first. That vector, point your index finger in the direction of that vector. Right? Okay, next. Second vector, in this case B. Here it is. Arbitrary choice. I'm going to have to use my middle finger. I'm going to have to bend my middle finger in order to get it to point in the direction of that second vector. Now, importantly, you can only bend your middle finger in the direction that fingers want to bend. None of this nonsense here. That's cheating, right? So index finger in the direction of the first vector. Notice I can bend my middle finger about like this, and that points that in the direction of the second vector. Is everybody with me? Okay, now that said, notice that between the two of them, A and B, they define a plane. This third vector points generically on one side or the other of the plane. With your hand arranged as previously discussed, your thumb points on one side or the other of that plane. And again, no breaking your joints, right? So as I have it here, notice my thumb is pointing on what you might call the upside of that plane. That third vector, C, also pointing on the upside. And that's what we mean, because it's my right hand that makes my thumb point in the same direction as the third vector. That's why we call this a right-handed list. Everybody follow? Index finger parallel to the palm in the direction of the first vector. Middle fingers bending the way middle fingers want to bend. Which side of the plane does your thumb point onto? Okay. All right, that's a right-handed list. Now again, there's nothing magic about those arrows that I drew here. I could conceivably ask about, what did I erase that for? I could conceivably ask about same list of vectors, A first, B second, C third. What if this was A and this, whoa, that was the worst two I've ever made. That is B and this is C. Let's try to play the game. Let's see if this is a right-handed list. Now I'm going to have to come over here and point my index finger in the direction of A. And now notice I have a problem with B. My middle finger doesn't want to bend that way, and I'm not allowed to cheat like this, right? Notice, though, my index finger can point toward A in a variety of different ways, right? I'm still pointing in the exact same direction. I can sort of turn my wrist around kind of however I want, and in particular, if I hold my wrist like this, index finger still pointing toward A. Now, my middle finger bending the way it wants to totally points in the direction of B. Everybody with me? So we're 2/3 of the way there. We got A, we got B, but check it out. My thumb is now pointing downward. C is pointing upward. My thumb is pointing on the lower side of the plane. C is pointing on the upper side of the plane. This is not a right-hand order. My right hand can't do that. Right hands, in general, cannot do that. Left hand, no problem. Everybody see it? Okay, so that's why this is a left-handed list. This is a right-handed list. Okay. All right, and again, annoyingly, there are anomalous, weirdo cases like, this, for example, and what if one of the vectors was 0? What if two of the vectors were parallel to each other? Different sort of ways that a list could end up being neither right-handed nor left-handed. All of those cases are linearly dependent, and so I'm just going to lump them all together and call them dependent. Is that cool? All right, so I claim, not obvious, but I claim that this right-handed versus left-handed geometric description of a list is totally analogous to clockwise and counterclockwise. After all, what was it that really characterized clockwise and counterclockwise as being natural? Well, they're mirror images of each other. You trade any two vectors and that changes the listing order, and it's independent of rotations. And I claim that all of that applies to right-handed, left-hand. right-handed and left-handed are always mirror images of each other, right? If you trade the position of any two vectors, and this is a good one to think through on your own, let's see here. If I trade the first with the second and the second with the first, right? What was right-handed originally, ABC is right-handed here, right? BAC is left-handed. Everybody see that? Okay. And lastly, doesn't matter if you rotate. And this is another one that's a lot easier to see, sort of literally the hand wave. If ABC is a right-handed order, and if you rotate those vectors some way, still a right-handed order, right? If I take my right hand and orient my right hand any way, it's still a right hand. Is that cool? Okay. All right. So the same exact three properties that clockwise, counterclockwise had, right hand, left hand have in 3 dimensions. Excuse me. Okay, there is another property that I think is worth mentioning. It's what I like to call cycling a list of vectors. If you take the third vector and put it where the second vector was, you take the second vector and put it where the first vector was, you take the first vector and it kind of falls off the side, and so you come back around and put it where the third vector was, right? Cycling in this way doesn't change the order at all. And there's an easy way to see. Oh, you have a question?
Yeah. Does the third vector in the list always have to be perpendicular to the plane?
No, it doesn't have to be perpendicular. It's just a question of which side of the plane is it on. So if I have a plane like this, right, there is an above side, if you will, and there's a below side. Or if my plane is like this, then there's this side over here and that side over there. So it's just a question of whether the third vector and your thumb, do they point on the same side or do they point on opposite sides? That's all. Yeah. Okay. All right. Okay. So, yeah. Cycling preserves order. Oh, and yeah, you can see this. Let me see if I can remember. This is a little confusing. Okay, so ABC is right-handed order. There's ABC in right-handed order. Right? Now I'm going to put B. I'm going to show that BCA is in right-hand order, like this. This is the little hand gesture, right? ABC right-hand order, BCA right-hand order. Everybody happy? Okay. All right. All righty. Okay. So. Next, here's a theorem that you might have seen in a linear algebra class. This is about determinants. I know you all have seen a lot of stuff about determinants. There's a lot more to say about determinants. It may be that your linear algebra class is focused on sort of more algebraic properties of determinants, and that's fine. This is a very important geometric property of determinants. Starting with the two-dimensional case. Suppose you have a list. Whoops, I wanted purple here, sorry. There we go. Suppose you have a list of two vectors in R2. Okay. That pair of vectors in R2, I claim, makes a matrix if you think about it, because the first vector, I could just choose to make the first column. The second vector, I could choose to make the second column. And so given a list, there is implicitly an associated matrix, like so. Okay, but wait a second. When you have a matrix, then you can make an associated linear transformation. And then, wait a second, I claim that you can also then make an associated parallelogram because, after all, the image of the first standard basis vector. Now, reminders to what we talked about Monday, I think it was. The image of a standard basis vector is the corresponding column of the matrix. And so the image of E1, first column, is the vector A. And then likewise, the image of E2 is, it's the second column, which is the second vector, which is B. Is that all right? Everybody okay? Now, I haven't actually stated a theorem yet. I've just made the observation that if you give me a list of vectors, I can turn that into a matrix, which I can turn into a linear transformation, which I can turn into a parallelogram, right? I haven't made any statements about these things yet, but I'm just pointing out, you give me a list, I can make these things. Is that cool so far? And now I'm going to start actually saying stuff about these things. Really surprising result. This first statement right here. Let's see here. Here it is. The absolute value of the determinant gives you the area of the parallelogram. It's really weird. So now to be explicit, I guess I should use purple. The matrix that I inferred from the list and the parallelogram that I inferred from the list are related in this way. Determinant, absolute value of determinant, gives you area. You buy it? Yeah, question.
Sorry, real quick, what is S supposed to represent?
S is the unit square.
Okay.
So it's S for square. That's all. Yeah, because the edges are E1 and E2. So yeah. Okay. I want to emphasize this fact here about the absolute value of determinant giving you area. Way not obvious. In fact, it's not only not obvious, I would call it counterintuitive. Not only does this not look true, I think it looks false. Let me explain to you why I think it looks false. How would I normally, if this were a high school class, how would you compute this area? Well, you'd drop a perpendicular here, right? How would you compute that height, as it were? You compute that height with some trig. Where's the trig? Determinant doesn't have any trig in it. Determinant's just three-function arithmetic. It feels like the formula on the right should have some trig in it, and it doesn't. Seems pretty sketchy to me. Secondly, the base, the length of the base here, the magnitude of the A vector, involves a square root. Where's the square root, right? Determinant doesn't have any square roots in it. I think this looks highly suspicious, right? If I didn't know this were true, I wouldn't believe it. Yeah? It's mysterious that it's true, but it is true. This fact, by the way, is a little bit hard to prove. It's not so bad. By the way, this is one of the proofs that I'm going to be leaving out. You'll furthermore notice not only am I not going to walk you through the proof, I didn't even write down the proof here in my notes. It uses a couple of ideas that are just a little bit beyond what I think would be reasonably accessible in this course, and so I'm just not going to do it at all. Okay, but I claim this is true, counterintuitive though it is. All right, let's see here. Next. I need to zoom out so we can fit all this in here. The sign of the determinant of the matrix, and keep in mind, we're still talking about this same matrix. The sign of that determinant, whether it's plus or minus, tells you about the order of the list, namely whether this is counterclockwise, as I've drawn it here, or possibly clockwise if these were different vectors. But whether or not, which way it goes, whether A to B, this original list, A to B, whether that is clockwise or counterclockwise is entirely decided by whether the determinant is plus or minus. Seems like a magic trick, right? Certainly not clear why that would be true. But it is. And again, sophisticated proof, not appropriate for the class. Okay. All right, is everybody on board? Yeah, question?
If you're trying to find the area of the parallelogram,
yeah,
does it matter which vector is first or second?
It doesn't, because whichever you do first or second is only going to make a difference in, certainly the parallelogram itself doesn't change, right? So which one you write first will account for a minus sign in that determinant, right? But as far as area is concerned, we're going to take the absolute value anyway, so it just doesn't matter. But it does, of course, whether A or B is first or second, it does affect the order. It does affect the plus or the minus of the determinant. Yeah. Everybody with me? All right. Okay, so now specifically, how does it do this? It does it as follows. Positive means counterclockwise. Negative means clockwise. Again, I'm not going to prove this, so don't look for the why. I'm just claiming that this is true, and you need to know that this is true, but you don't need to know why this is true. Positive means counterclockwise. Negative means clockwise. And then there's this annoying third possibility of, it could be that the determinant is 0, namely neither positive nor negative. That would result in neither clockwise nor counterclockwise. In other words, dependent, which would correspond to these two vectors being parallel, or one of them's a multiple of the other, or one or both of them are 0, or something annoying like that. All right. Okay, now let me talk about this other point of view here. Sign of the determinant still. Instead of thinking about whether this list A to B is clockwise or counterclockwise, I claim we can interpret this as telling me whether the plane got inverted or not. And what I mean by inverted is that, if you have a linear transformation, of course that might involve some stretching or some shearing, right? Or a rotation, some combination of these things. If you think about it, stretching preserves order. Shearing preserves order. What was the other one? Rotation preserves order. But it could also involve a reflection. Reflection does not preserve order, right? A reflection would turn, I have to do this from y'all's point of view, clockwise, okay, this is hard, clockwise into counterclockwise, right? Clockwise into counterclockwise. Does everybody see what I mean? Yeah. Okay. All right. So, so again, you can think then about what this is doing is this is telling you about whether this linear transformation flips things over or not. And for example, let's think about what we have drawn here. Notice E1 and E2 are counterclockwise. That's always the case, right? E1 is always this. E2 is always that. So the list E1, E2 is always counterclockwise. So if you take counterclockwise and you do a bunch of stuff and the result still counterclockwise, there was no reflection involved in that process. There could have been a rotation, there could have been a magnification, a stretch, a shear, whatever. No reflection. Does that make sense? Whereas on the other hand, oh gosh, again with the button. Another possibility, what if this were A and this were B? Now keep in mind, A is still the first vector in the matrix. A is still the image of E1. That means this is the first vector. And likewise, B still the second. B still the image of E2. B, if it were over here, would be this. And now notice this function T here, is now turning a counterclockwise list into a clockwise list. And how could that be? Right? What if you have a clock face that you're looking at, right? The clock face is going like this, as you know, seen from y'all's point of view. Stretching it's not going to change the fact that it's going clockwise, right? And magnifying it or shearing it is not going to change the fact that this is going clockwise. I would have to flip it over. So when the determinant is negative, one way to say it is that this list is clockwise. Another way to say it is that this linear transformation has a flip embedded inside of it, right? A reflection. Things are getting turned over upside down. Anyway, alternative point of view. Okay. All right. This is a three-dimensional version of that same statement. And again, I like starting with the two-dimensional version because it's a little bit easier to see, a little bit less geometrically difficult, a little bit more intuitive to see in the two-dimensional case. So, but here's the three-dimensional version. And again, if you have a list, you can make a matrix. If you have a matrix, then you have a linear transformation. If you have a linear transformation, you can look at your standard basis vectors and see what their images are. E2 goes to B. Oh gosh, I didn't mean to do that. And then E3. E3 goes to C. And all of the expected analogous statements all work. And I'm going to have to zoom way out to fit this all in on the screen. Determinant of this matrix gives you the size of this parallelepiped, size in this case being volume. So it's volume instead of area because it's three-dimensional instead of two-dimensional. Absolute value of determinant gives you that volume. The sign of the determinant tells you whether this list over here is right-handed or left-handed or dependent. Positive means right-handed, negative means left-handed. 0 means dependent and something weird happened. And furthermore, right-handed and left-handed, keeping in mind that these standard basis vectors, that's always right-handed, right? Let's see, let me highlight here. If the determinant is positive, and that means that this list over here is right-handed, well, then this linear transformation turned a right-handed list into a right-handed list. So it's some combination of rotations and stretches and shears, but no reflection. And so there is no inversion of space in that case. And then turning it around, if the determinant were negative, then this would be a left-handed list over here. What could possibly turn a right-handed list that you start with and turn that into some sort of a left-handed list? Right? How can you do that? How can you turn a right hand into a left hand? Well, you can rotate all you want and stretch and shear, and that right hand will stay a right hand. The only way to make a left hand is to have a reflection involved in there somewhere. So again, alternative interpretation of the sign. You can think of the sign as commenting about the list of vectors. You can also think of the sign as telling you about the transformation itself, geometric features of the transformation. Okay. All right, so let's see here. I've got a minute and 6 seconds left. I want to make a real quick reference here. This will just take a second. Nice end of a page. Whoops. We're going to define something called a cross product. Cross product of two vectors. It's this formula right here. It seems weird and arbitrary. I guess it is. Different way to think about this, and I encourage you to think about it this other way primarily. You can think of it as this, what I'm going to call symbolic determinant. And I know this is weird looking, but notice A goes there, and B goes there. And then all you have to do, now this is, again, creepy looking, but put E1, E2, and E3 there as if that makes sense. Wait a minute, Can you do that? Can you? But this is supposed to be a matrix. What I have right there is supposed to be an element of a matrix. It's supposed to be a number. I've got a vector where a number ought to be. That's nonsense. It's bogus. Can't really do that. So if we ignore that nonsense, if we pretend that this makes sense, treating this only as just little symbols and computing determinant, just based on where the symbols are written, and just kind of ignore the fact that this doesn't mean anything. Amazingly, this will give you the exact right formula, and it is super handy. So this is, it's again a little bit garbage, but super handy. And in my life, I memorized this formula really quickly because it's so easy. This formula here, I've never memorized ever. And if I don't need to know it, then you don't need to know it, okay? So I would encourage you to look at this only as a matter of being explicit. This is how you want to think about it. This is how you want to compute it. And this is a great place to stop for today. Y'all have a good extended weekend. See you on Wednesday. Yeah, sure thing.